Just to check, can you all see my screen? So I've got two screens here, and I want to check you can see the slides and not the presenter view. Is that
we can
good?
see your presentation.
Excellent, excellent. So just to start off, Katerina sent me this slide. So Katerina, would you like to say something about it? Because I think you're giving a talk here, so you probably have more to say. You're on mute.
Now I'm unmuted. Okay, thanks, Thomas. So Joanna Jordan, who is one of the organizers of this event on Newton by Newton Gateway Mathematics, 26th to 28th of April, asked me to promote this event at our mini symposium. It's a very fitting venue, of course. So it's a free registration, and it's a series of very interesting talks by many experts on transmission. I'm going to give a talk as well. So yes, shameless promotion, I guess. Sorry about that. So anyway, I hope you register for the event. Thank you. Bye.
No, no problem. I mean, that's all we have as academics, is shameless promotion. So to carry on to my talk, what I will be talking about today, well, thank you to the panel for inviting me along to give this talk. What I'll be talking about is a few side projects that my students have been looking at. They're just small things but I think they're really quite impactful. I'm always looking for the short, quick, understandable question that can really help someone. Not to say that the big overarching questions aren't important, but I'm not getting paid for this, so I might as well do the small questions that can be answered quickly rather than the big research topics that I don't have the students for. But after the small projects, I'll get into a bit more of the detail about an individual-based model that we've been looking at, which has been feeding in from the work that Katerina and Ian's group have been doing with the idea of how do we combine the aerosol modeling with the individual-based infection spread. So the first piece of work that my students, Lucy, Josh, and Tim, they're three great students. Look out for these guys. They're going to have some great careers ahead of them. They applied to do a NERC hackathon. The hackathon had a £3,000 prize to look at the effects of COVID on the environment. Now, I'd like to say they were doing this altruistically because they want to save the environment, but we all know it was because of the £3,000, and they actually won. So, you know, all well, good to them. What they were looking at was the NERC had a lot of data, and they said, do something with it. We don't know what you can do, but please do something with it to help us understand the impact of COVID on nature. And what they looked at was they took a ground plan, a floor plan, a seating plan of a class 150 diesel train. The plan you'll see here, those little marks there are the seats, and the little black dots are where they say you should sit. And they actually not only, the details there give you the full details about the project, and the app interface gives you this app. So you can put in things like shielding, number of shields, length of shields, social distancing rules, and it will spit out in real time the optimal seating for the public transport. Specifically, what they were looking at was public transport is most efficient when it's packed full. You know, the more people you can get on your bus, the more efficient it is because you're spreading the carbon it's producing amongst all those passengers. But because of COVID-19, we have to be separated by 2 meters, so you can't pack a diesel train full. So how does that affect the environmental impact? I've got some flashing here. There's something in the chat. How could this seating be implemented practically? Good question. I will get onto that. So they have this floor plan. They set up a greedy algorithm. So it really is just place someone, knock out all the chairs around them you can't sit in, place the next person. And what's great is that you can show that in the basic setup with no shields or anything, 16 people is the optimum number of people you can fit on. And it's not just a local optimum, it is a global optimum, which you can show very quickly with some bounding arguments. But that's crucial because there's a graph on the side here, again, you'll see better in the interface of the app, is that the amount of carbon produced when you put 16 people on this train is unfortunately worse than the amount of carbon produced per person from a small family car. And that's only assuming that the small family car only has one person in it. So if you can fill a small family car with a family from one social bubble, of course, then your car is actually doing better than the train. So conclusion, get rid of diesel trains is obvious conclusion. But How can we do this practically? We actually got in contact with Transport for Wales and showed them this work, and it's with them now. I do believe they used it to help them, but I also believe what they did was initially they went out with someone with a tape measure and just measured 2 meters, and from then we've given it to them. I hope they're using it. The second piece of work we did was just before Christmas with Pearl Harper and again Josh. We looked at the number of secondary cases that would arise from students returning home from university. Again, stupid, simple piece of mathematics. Simple formula. The number of infections will be the number of students you have times the number of those that are infected, times the number of people in a house, times the number of people that will get infected in that house. We're not trying to, win a Nobel Prize here. We're trying to do something useful and quick. And again, there's an app here that the student Josh did. Again, watch out for his career. He recently gave the Light Hill Thwaites Prize talk. He was shortlisted, has a great future ahead of him. The app looks like this. You can fill in all the details about the probabilities of household size, number of students, and prevalence. And again, it will kick out in real time the expected number of secondary infections. So why I like this piece of work is because everything was parameterized. From Welsh government data, we can say how big a household was. So in terms of 2, 3, 4, there's 2 people in this household. One is the student returning home, and one would be a guardian parent. 4 people, it's 1 student plus 3 others. So, and then we go up to 6 plus from the data. We also have this data from Lopez Bernal et al., which tells us in terms of how many people are in your house, what's the secondary attack rate? What's the probability you get a secondary infection? We don't have quite a good comparison because the Welsh government data goes up to 6 plus, whereas the Lopez Bernal goes up to 5 plus. But what we did was for 6 plus, we said that they also have a probability of 0.25. So just to go back to the equation, we fixed the number of students to be 1,000 because we said, per 1,000 students, this is how many secondary infections we expect. Number of people in the household, we can't change that. That's from the data. Probability of secondary infection, can't change that. That's from the data. So all we really could do and play with is the infection prevalence. And that's really what only a university could influence. They could, how many people are infected? How many people are we sending home? And so what this work led to was the Cardiff University ramping up their testing in the last few weeks and then doing a staggered release. So if you got your negative test, you were then allowed home to try and reduce this idea of sending infectious people home. And the reason was because what we did was we did a Monte Carlo simulation. We didn't actually use this formula explicitly like this. We simulated 1,000 students, sampled from the household distribution, sampled from the probability of secondary infections, and built up the distribution like that so we could get error bars on the number of infections. And that's what we're seeing here. So these are just 2 infection rates, 2 realistic infection rates, because at the beginning of term, last winter term, last autumn term, the infection rate went up to around 15%. It was really tearing through the student population. But by the end, it was around about 1.5. And what we were saying is that if we put a 1.5 or a 0.015 chance of being infected in, you've got 15 people, which is roughly 1,000 times 0.1015. If you have the infection prevalence of being 0.15, then you'd expect around about 150 people, secondary infections, to be infected. Again, 1,000 times 0.15. So what's happening here? What can we understand from this? And again, it comes directly from the equation. The bits on the left, the number of students times infection prevalence, that's simply how many infected people are you sending home. The bits on the right, the number of people in a household, probability of secondary infection, that's the number, that's like a local R rate. It's the number, the probability of infecting another person in that house. And what you find from the data is on average, that's around 0.94. So what we're saying is for every infected person, as a rule of thumb, every infected person we send home would infect 0.94 others. So every infected person you send home, you would get a second infection. And that's why you're seeing this. So if we send 15 people home, they infect 15 people-ish. We send 150 people home, they infect 150 people. But again, not what we're here to talk about today. We're here to talk about the more individualized simulation that we're doing. And to give you an idea of what this is based on, we're looking at a population, a large, well, it's individual based. So when I say a large population, we're looking at 200 people-ish, on the order of 100, a few hundred. And we're saying that that population can be broken down into subgroups. So what we're thinking about is maybe a classroom where you have 30 students in your classroom, and then each of those students are on a table of, say, 5. So you'd have 6 tables of 5 students. That makes your entire population. Or we've also applied this to a halls of residence. There you've got around 200 people, and we're looking at kitchen groups, people who share the same utilities, whether they, it may be bathrooms or kitchens. But it all comes down to this idea that you have a population of n, and we're grouping them into a smaller group size of ng. Because what we really want to understand, and just to give you an idea of where this is going, is what happens when we isolate people? Well, we were working with the Welsh government on this piece of work, and they wanted to know, should we isolate anyone? Should we isolate individuals? Should we isolate a small number of people? Should we isolate everyone? And this gave us a route to answering that question. So the initial infections are estimated using the local background prevalence. So if there is a community prevalence of 2%, we infect the class at a rate of 2%. And what we're really looking at is how those secondary infections spread. So again, we take the idea that from the data we have an R number, that gives you an idea of how many secondary infections should arise. But what we're trying to do, what I would say our novelty of this work is coming from this idea of how should we split that between the local infections versus non-local infections? And this then comes down to an idea of how do masks and ventilation affect these inputs, which comes from the work of Katerina and Ian's group. But it's really this, essentially, you can think of it as a crude way of modeling space. We have 2 spatial compartments, local and non-local. It's an individual-based model, so we can attach many properties to each individual agent, and we have many parameters. Here's just a selection. We have, because we're dealing with students, young students particularly, many of them are asymptomatic, so we have a symptomatic probability. We have compliance. For school settings, secondary school settings, compliance is thought to be 100% because they control who they let in. But for university accommodation, we've had it from the Welsh government that compliance is around 81%. For each infected person, we attach 3 times to them. 3 days. Again, one thing I'd like to say is, if you're angry about some parameter values, I don't care. I'm making the engine here. We've made it very flexible. And if you've got a new set of parameters you want to try, fine, we can show it in. Because what we're trying to do at the moment is get some funding to create a calculator, because we're working with these policymakers. And the worst thing about working with policymakers is once you do the simulations they want, they'll always say, oh, but what about if it's 0.81 or 0.82 compliance? Doesn't matter. So what we're trying to do is we've got the engine running, create a computation for them that they can fiddle around with the parameters to their heart's content, particularly understand the sensitivity of the simulation outputs to these variation in parameters. So anyway, as I was saying, once you get infected, it's 3 days to become infectious, 5 days to become detectable. So you have 2 days in there where you're infectious, you're infecting other people, but you cannot be detected by lateral flow devices. That's what we were particularly looking at. And then 10 days after which you become recovered. If your agent becomes infected and detectable, and they are detected by a lateral flow device, we remove them from the group with a probability that reflects their compliance. And if they become susceptible, they remove themselves, subject to compliance. This sort of infographic gives you an idea of the macroscale level of the simulation. So you put your people in at the start of the day, all those who aren't isolating. And what's great about this simulation is all these boxes are modular. We can extract and turn on and off all these boxes. So some days you may want testing, some days you may not want testing. And that testing occurs before these people are allowed back together. So again, we can turn mixing off and on. In a school, we mix every day except weekends. In the halls of residence, we can mix the students every day. The infection stage, again, that's coming down to, I'll explain in a minute. It comes from the work done by Katerina and Ian. And then there's the symptomatic removal. So if throughout the day you become symptomatic, we remove those, you isolate, and they don't return, subject to compliance. Now, as I said, that was the macroscale, that was the nice overlayer. The actual algorithm is doing something much more complicated, and this is given by this flow diagram here. Now, I don't want you to try and understand what's going on in this flow diagram. It's very big, it's very complicated. what I want to highlight is this section here, which is where the aerosol work is coming in. Because what we're trying to do is, based on how the air spreads the disease, what's the probability of the local infections versus what's the probability of the non-local infections, and how do masks and ventilation change those? So this huge computational, very complicated, I've got to say it's not my favorite way of doing this, but it's what the policymakers wanted, and so we give them what they want. We can affect all of these ideas when people mix, when we test, what interventions we apply, and how they affect the simulation, how we isolate, who we isolate, when we isolate. And as I've said, we've got parameters that affect the number of asymptomatics and their compliance. Don't have time to talk about all our results. So if you're interested, there is a preprint here. Please do go have a look. That goes into more detail about everything I've said. I'm going to mainly focus on the secondary school simulations, but as I mentioned, we also do schools of residence. So in terms of the secondary schools, what we're mainly looking at is who should we isolate? Should we isolate no one, an individual who's ill, their table group, or the whole class? The compliance is 100%. The local and non-local infection rates are modulated based on the ventilation and mask probability that was just spoken about in the previous talk. And the mixing only occurs on weekdays. Now, as I say, this is a big simulation, big black box simulation. We set it up, we let it run, and we can get all the data you would want. But we're working with policymakers. They can't handle all of this data. So I'm showing it here, but don't try to understand what's going on. We can get out a number of infections, number of recovered, number of isolations. If you want that, we can get it. But the policymakers want a simple metric. Particularly what we're going to do, and I'm going to show you some graphs here, and I want you to learn how to read the graphs before I tell you what the graphs mean. What they wanted to know was how many, after a month, after 28 days, how many of my classroom are going to be affected, and how many days loss per individual would we expect. So we've got a scatter diagram here showing interventions. So the colors represent interventions. Black is no intervention, mask is red, blue is ventilation, green is both. The transparency of the color is then how much testing there is. So a full color is no testing, and as you get more and more transparent, you get more and more testing. Now, what I should mention is each of these points is not a point. It's actually in itself a pie chart. So you're actually seeing about 5 dimensions worth of data here. So it's a complex graph to read. Each pie chart is representing the proportion of infected isolations versus those you isolated who are not infected. So for example, if you're looking at this right graph here, this full black circle here, well, the black pie chart is that there's no testing, there is no intervention, and we're probably isolating 60%. 60% of all the people we've isolated are actually infected, where around about 40%-ish are isolated and not infected. And as we test more, we isolate more people who aren't infected, because what we're doing there obviously is we're isolating maybe a table group. I'm not going to explain what's behind these. I'll explain what's going on in later graphs. But like I say, I just want you to understand what you're seeing before I start explaining the graphs, because what I want to show you is we're going to start putting a lot of data on these graphs, and it's going to be coming down to how you understand them. What's on the head of each graph is some parameters, the R value. Hopefully you'll all have a grasp of what that means. PS, if you remember, was the symptomatic probability. So here we have 20% of the infections are symptomatic, 80% are not. And PFN is the false negatives. That was one of the key ideas behind the lateral flow devices, was they have high number of false negatives. We've gone from 20% to 50%, something like that. So that gives you an overview of how to read these graphs. So let's actually interpret some of them. Again, we won't have time to go all through the results, but let's have a look at isolation to begin with. Through 4 graphs here, increasing number of isolations. And what I should say now is I'm not going to surprise anyone with any of my results. These are, standard results apply, and this just backs up all the work that's been previously done. If you isolate everyone, it's like a fire break. You find one person in your classroom who has COVID, you tell the class, go home, 10 days, recover, everyone comes back. you stop the infection spreading. Low number of infections, high number of people missing classes, and also a high proportion of isolations that aren't infected, as expected. And at the other end, if you don't isolate anyone, your class completely gets wiped out if you don't do anything. However, this insight will carry over through all simulations. Essentially, the hierarchy is testing is good, masks are better, ventilation is best. And of course, mixing those together gives you better performance. But ventilation is best because it does a double whammy of impact to your population. And it is that it removes some of the particulate matter from the air, as well as it stops spreading. So you're reducing your local infections because it's removing stuff from the air, and it's greatly reducing the non-local infections because it's stopping the disease getting to those non-local infections. So that's the first one. And here we go with a bit more detail. This is when I start ramping up the complexity of my graphs. Here what we see is we're mainly looking at what's the impact of testing. We're now putting testing. Previously we had no testing. It was just all about isolation. Here we're now putting some testing in as well as isolation. And what you see, testing does help. You know, your points move to the left, so you're reducing the number of number of infections over the 28 days. But if you compare your black points to your red points, you're gaining as much benefit from just telling your people to wear masks as you are from testing daily. And of course, again, putting ventilation and masks together is always the best. Ventilation, it always helps you most because, as I say, it removes stuff from the air and it reduces the number of non-local infections. But always, I don't have an agenda. I've created this engine, we put the parameters in, it spits out the results. It's then up to the policymakers to say, well, where do I want to be within this parameter space? I could isolate everyone, but that means lots of school missed, lots of people being isolated who aren't infected. So you'll get a very unhappy group of people. Or I could isolate no one. I could let the infection spread through. But we then do have a lot of people getting ill. Not up to me to say where we should hit. That's purely policy. So let me conclude with 10 seconds left. I love simple models. As you saw at the beginning, greedy algorithms, simple formulas, interpretable. We have the data for them. Very useful, very short-term, very useful, can help us understand what is the next best move. Testing is good, masks are better, ventilation is best. Hopefully I've not surprised anyone with those results, but it's always, policymakers always like to see something that will help them make and understand something that fits with what they already know. And with that, thank you very much. Please, any questions?
Thank you, Thomas. We have a minute for any questions, which could be for Thomas or they could be for